Hello, everyone. Thanks for coming. And today I'm going to talk about pushing the performance and usability of zero knowledge proof. It's a joint work, you know, of over 10 people. It's Morgan, Daniel, Marty, Ellen, Michael. Just wanted to highlight the authors. Um, Table of contents. So I'm going to go through like why we're building a ZKVM, what are the methodologies that people have been trying, why we think ZKVM is the future direction, and what are the limitations with existing ZKVMs. There are a couple, Cairo, Risk Zero, MIDEM, and how we are, what we are doing to build the fastest ZKVMs and how we're optimizing the prover, ZKVM, the compiler stack. And then I'm going to show a demo and benchmarks of the current VM. Um, so I guess the motivations behind ZKVMs is how do you prove succinctly and in zero knowledge that a certain program was executed on a certain input and it had a certain output. Um, and succinctness means that proofs are not too long, and zero knowledge means that the proof contain no useful information beyond the facts that they're proving. And the problems that in this space is that first one is the learning curve of the tooling is really steep, and then the second is the high time, space, and energy cost of creating zero knowledge proofs. Um, so these are three, I guess, compilation approaches that people have been trying in this space. The first one is DSL. I think most of the people here are familiar. Socrates, Circon, a bunch of other languages are taking the first approach. It's basically an attempt to use domain-specific language to build abstractions on top of low-level constraint systems, such as R1CS or Plonk, acting like constraint writing macros. The second approach is direct approach. Is actually a project worked by Anoma called, I think, Juvix, and Chris was leading the project. So they're trying to directly compile high-level programs to circuits directly without an intermediate instruction sets. The third approach is, I guess, the instructions sets and VM approach, which is to define an intermediate virtual machine and instruction sets architecture to mediate between the high-level language and low-level ZK constraint systems. And all of them are actually trying to, I guess, like the first approach, all of them have advantages and disadvantages. I listed some that we think are, the pros and cons. And for DSL, it's really easy to build abstractions on constraints and allowing for a closer reasoning about performance, circuits performance. Direct approach, I personally don't know that much, but I think it's potentially very, very high performance because it doesn't lose information to IRs, and it's easier, potentially easier to verify. And then VM approach is definitely developer productivity, right? It allows for the use of higher languages, higher level languages that are more familiar to developers, and those are the three approaches. And we think that because of mainly two reasons, development, productivity, and security, that ZKVM is the dominant way that developers will interact with zero knowledge. Okay, limitations with existing ZKVMs. These are too small, the texts are too small, but we're basically listing some issues with, I guess, Cairo and Risk Zero. For Cairo, I guess it's mainly about developer productivity, writing Cairo code, inexperience among like auditing firms, and runner performance. Because of non-determinism handling, Cairo has some like fundamental limits on the runner performance, and there is no. I'm not sure if it's still like closed source because I heard Stone Prover is open source right now, but a couple months ago there's no like open source prover, and it's hard to support smaller field like 31 field. for Cairo. And then for risk0, it's mostly like, oh, there's no open source recursion, constraints are auto-generated, and the code generation is not open source. So it's really, it's make it impossible to fork and modify and add modules, I guess. And it's also cannot be easily changed to support a smaller field. Okay, there are bigger text. So Cairo's limitation, risk-less limitation, and then the common issues is the 31 bit field to improve proof of performance. Right, so I guess in conclusion, Maiden stack is stack-oriented design, and it's probably less efficient due to the heavy stack manipulation. And Cairo's architecture is unsuitable because of its unusual memory model and lack of essential built-ins, co-processors. risk0 is, we think, is a better option than Cairo, but it's not the ideal for proof of performance because it's conforming to RISC-V architecture, and it's not that snark-friendly. Okay, so we need a ZKVM that's much more extensible, performant, and developer-friendly. That's basically what we've been working on for the past a year or so. And I guess these are the steps to build this ZKVM. And the first one is we chose and built a base proving system. It's called Plonky3. It's collaboration efforts between Polygon and us and some open source contributors. And the second step is to build this ZKVM with the ZK-friendly instruction sets that are tailored to maximize proof of performance. And the third is to create a compiler toolchain. And we're using LVM IR. So we're writing this LVM IR to our VM's compiler, allowing for high-level languages to compile on our ZKVM. And the fourth and fifth is like hardware acceleration and formal verification. So optimizing for prover VMs and compiler. There are some, I guess, the slice is just trying to say like, what are some of the questions that we were thinking when we were designing this? So the first, I guess, is like, of course, tricks to maximize proof of performance that's on the Plonky3 side. And I'm not going to talk about Plonky3 today, I guess. There's another, I guess, leading question, problem is there's a difference between ZKVM computing environment and hardware computing environment, and that can drive and derive different instruction sets design decisions. From compiler to the ZKVM ISA side, as one question is like what instructions are more efficient to include, and to check in the stock constraint system what instruction sets are more efficient to exclude from the ISA and eliminate from the compiler output by replacing them with a sequence of instructions. So those are the questions that we're thinking about when we are designing the ISAs and designing the stack. So Valida instruction sets is a ultra risk, I'm not sure if it's a term, but it's like an ultra reduced instruction sets. It's modular and it's a ZK friendly instruction sets. And it includes basically the following modules. Includes 32-bit LU chips, and includes a CPU chip, memory chip, program ROM chip, and then an 8-bit RAM checker chip. Here's a cute diagram about Valida VM was talking about. This is the ALU chip with add bitwise equality and quality logical shift left and right and stuff like that. And there are some like traits of the ISA. So for example, is we have 2 special purpose registers, program counter, frame pointer. There's no general purpose registers. And I want to take this as an example of, so how we were thinking about this is that it simplifies code generation by eliminating the need for a register to be saved and restored in the calling convention, and eliminating the need for register spelling code to be admitted. And then it's 2 RAM addressing modes, blah, 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 and its program ROM can be addressed. This is the last slide about ISA. So there's no dedicated stack pointer register, and the calling convention uses constant size stack frames, and variable sized locals and arguments will be held on the heap. So the VM overview is it works as all the other ZK VMs. It has an execution engine which runs Valida programs and generate execution trace. And then there's a prover that proves the result of executing a program by proving the existence of that valid execution trace. And then the verifier verifies the result of executing a program given a certain proof. So it's 3 components. And some basic parameters about Valida ZK VM. So we're right now using a base, our base finite field is, we're using Baby Bear. I think we're working on Merson field, Merson 31, and they're using Fry PCS right now. We're also integrating with Basefold, which is a paper recently published by Haras, who work with us. And also breakdown, but we were still thinking about the pros and cons there. This is, I guess I talked about this before. So the prover, I don't think I need to go over all of this. It's just like telling you like how the prover is generating the execution traces and I guess the procedures. I can pass this really quick. Okay, so the techniques of those, I guess I want to go over this because, so 2 main points is that this proving system, the Plonky3, is very efficient, and the most expensive crypto primitive it uses is the hash function. And so our VM uses gate with degree at most 3. We're trying to keep FFT and hashing costs as low as possible. So that's, I guess, technique number 1. Number 2 is we're using this finite field that's really efficient. So it's Baby Bear and Merson field. That's number 2. So that's, I guess, the main takeaways for the optimizing the prover side. And then like the final step is the LVM compiler that we're writing. This is just to show you sort of the process. The main takeaway is like we're planning to support all the front ends that's supported by LVM, C, C++, Rust, and Go, and other languages. So this is basically compiling the LVM IR to our VM's assembly. This is the compiler overview. So from C to CLAN to LVM IR to LVM optimizer to our Valida backends, and then to our VM's assembly. So Valida's implementation, I guess 2 main advantages except performance is that application builders can use the included compile time macros to generate a Valida VM and prover based on sort of a set of chips customized for their use case. So if you're building a ZK VM, you can choose like, oh, well, I want an acceleration circuits for key check function, hash functions, and you can add that. So it's really like a modular, customizable design. And then it's also fully open source. So the VM is dual Apache and MIT license. I think we are probably like the only one, or if not the, I guess it's a fully open source. Please check out the repo and feel free to contribute. So I'm gonna run like a demo of a Fibonacci program, and oh yeah, thank you.
I'm Morgan Thomas, Applied Cryptography Researcher at Lita Foundation. I'm here to demonstrate for you the Valida ZKVM prover. I'm using an example which computes the 26th element of the Fibonacci sequence using a simple iterative algorithm. This example has been handwritten in Valida machine code. You can see here the Rust code that generates the machine code, and code comments describing the assembly code for this program. The rest of this program here just instantiates an instance of the Valida ZKVM prover and proves the execution of the program. So let me show you that this is built. There you go. And let me run it for you. I'm going to run this example in single-threaded mode. So there it is. So this time it took about 0.08 seconds in user time or CPU time to run, and about 0.09 seconds, about the same, in wall clock time. So for comparison, computing the 26th element of the Fibonacci sequence in RISC-0 using RISC-0's own benchmarks, I found that to be about 33 times slower in terms of wall clock time on the same machine, and it was running in multi-core. It took about 933 times more CPU time or user time on the RISC-0 side to compute the same answer.
Okay, so here are the benchmarks. So what Morgan was demonstrating is this iterative Fibonacci, and the depth is 25, and I think we're 933 times faster than RISC-0, and RISC-0 is using like a matrix function, which is like a bit atypical for like a Fibonacci program. So there is like a slightly difference in like the algorithm. So it's not 100% exactly the same algorithm, but I guess this is the benchmark for iterative Fibonacci, and this is for recursive Fibonacci. Anyway, so I'll pass this. Okay, so ongoing work. I mean, this is what we're working on at the moment. So we were still like reconsider the implementation of breakdown. We were thinking about using breakdown, but then we were still thinking about because it has slower recursion, etc. And then yes, the second is a vectorized implementation of sort of hash functions. And the third is we're trying to optimize Fry using some techniques. And then the fourth is we're investigating alternative memory arguments to handle the long memory traces that are more efficient in Plonky3. Then fifth is I was talking about the basefold PCS, and we're implementing that and integrating that into Plonky3. And these are the ongoing work. So I guess like we're also building this developer platform that we're trying to make it easier for developers to develop and improve and deploy. So this is a platform that you can use it to create new projects, and you'll be able to choose sort of different templates. This is like language templates, but we're also writing a lot of application logic templates that you can use. So here are some examples of the templates that we provide. For example, we're providing this consistent SDK or like client or X SDK, and you can leverage the SDKs, build your projects, and you can prove locally about the cost to measure the cost of the proving, and be able to deploy your projects using the platform. So you'll be able to choose the configurations, the hardware configurations of the VM you want to use, choose the approved aggregation layer you want to use, and the network you want to deploy. And so this is the another developer interface that we're working on as well. So I guess that last slide is Valida is an extensible, performant, and developer-friendly ZK VM. And yeah, thanks for everyone. So we have an early access program. You can sign up on our website. It's free, and it's give you early access to the VMs. And we can also help design and validate your product ideas. And we are hiring people. So we have this innovation team, which is right now has like one person, but we're trying to put together an innovation team to build interesting products, experiments, and we're looking for talented cryptography engineers and LVM compiler engineers. And if you're open source contributors, you know, talk to me, and you have mentorship from all the best like proving people in the field. I think it's going to be really fun. So this is our Twitter, my Telegram, and our website. Thank you.
And now we will have 5-minute QA time. So does anybody have question for Ventali?
Would a security audit be available for the stack in the near future?
Security?
Security audit.
Oh yeah, we haven't done security audits, and we're talking to a couple firms, and it's like hard for us to like find someone with like both LVM expertise and ZK expertise. So we're still
Right,
trying
right.
to.
You have to
Yeah.
audit both the compiler and the whole
Yeah.
stack, essentially.
Yeah. So yeah.
Yeah, two questions. The first one, I might have missed the answer. If you're not using general purpose registers, are you using, is it a stack-based machine?
It's
Like,
yeah.
Okay, so, but so if that is the case, what are you saving? I mean, if the argument against using registers is so that they don't have to be pushed on the stack, you are using the stack anyway, so I'm not sure exactly what is gained here.
Yeah, I can talk about this offline if you're
Okay,
interested.
no problem. Second question is about the comparison, like the benchmarks you shown. Um, from what I saw in the code, like the demo went a bit fast, and I don't know the library that well, but it seemed to me you were just hard coding the assembly in Rust.
Yeah.
And I would like to know when you ran when you compare to the RISC-0 implementation, there's a there's a RISC-V program. Was it also handwritten in assembly, or was it Rust, like compiled Rust, basically?
We're using their own benchmark, and their own benchmark is written in Rust, I think.
Okay, cool.
Yeah.
Thanks.
Do we have more questions?
I'm curious about, as you mentioned, that one of the advantage of Valida will be the code reusability, that the developer will not to need change their C or Go or Rust code. Is there any language limitation for the Valida implementation for now? For example, how will the Valida deal with something sort of that dynamic array or dynamic programming environment that if one of the developer want to implement that something sort the algorithm of digestra or something sort of that, how will the Valida deal with that?
Well, you're asking about language support?
Yeah,
Oh,
exactly.
Yeah, right now we are working on the compiler. Most of the C libraries are working, and then we're going to work on Rust and Go, and basically all the LVM compatible languages can be supported. And about the dynamic programming problem, we wrote like a note to this question, so I can send it to you like offline if you're interested. It's like a long conversation.
Yeah, thanks.
Do we have more questions for Ventali? Okay, thank you, Ventali. Thank you. And